Vou começar. All right, so good morning to everybody. On the behalf of the organizing committee for the PD session, Ricardo, Alonso, and me, I would like to give a warm welcoming for the PD session of the 30th Colóquio Brasileiro de Matemática. So let me do a couple of announcements before we start. We have many international students and professors and researchers here, so we'll try to keep the session in English so that we can contemplate everybody into the PD session. So the PD session will take place here in this Auditório 1. This week, this time, we are starting 9:30 every day. There are 3 lectures every day, and we are skipping Wednesday, so there is no lecture on Wednesday. So we try to keep talking in English. But anyway, I would like to see, just to let you know, feel free to talk in any language for the speakers, in any language that you like, that you feel more comfortable. There is no problem if there is some questions or some comments that need to be translated. We can help you with that, right? So once more, welcome to the PD session. So it is a great pleasure to me to introduce Professor Basilis Gidas from Brown University. Basilis is an old friend, has also very close connections with the math department of UFC, Universidade Federal do Ceará, and he will be our first speaker for this morning, and he will be talking about Monte Carlo simulation and optimization via inhomogeneous diffusions and renormalization groups. Basilis, please.
Thanks for the organizers. I guess there are 3 organizers, Eduardo, Diego, and Alfonso. And this is I think it is my second participation in the colloquium. So I'm going to talk about a subject that, sort of you probably have heard it, and you might have even in class, but I will give a PD flavor to that. And I will mix sort of the motivation and the mathematical theorems. I have 2 theorems to state. So let me start with posing the problem. I will have a function u of x. X is in Rd, or in some bounded set of Rd. Bounded. And it has, now, my D in some of applications is 512 by 512. That's the largest dimension where actually I did numerical calculations about the problem, of course, so specific u of x. In general, so this x has a special structure, and I want to give you an example. So the structure is you have a graph. So I will denote by lambda the vertices, and by epsilon its connector. So the graph that you shoot is the simplest graph. You have the Z2 or ZD, and I have a bounded subset of ZD, like in the square on the plane, I will have a number of sides. Let's say n by n, or 512 by 512 sides. And the x here has a structure xi, I in lambda. The xi could be in R or in higher dimensions, could be in S2, or could be in a finite set. So the whole thing, x will be finite. Now, when you have finite, you cannot write PDs, but we can write down Markov chains. Okay, so let me give you an example where the xi is here. And this example, actually, it's a real thing. We used it to construct topographic maps of Venus. In the middle 19th, there was a spacecraft that circled Venus and photographed with synthetic aperture radar the entire area almost 2 times. And then the geologist wanted to find the 3-dimensional structure of the surface, like mountains, valleys, and things like that. So the U, so then I, so I will be in lambda, like in there, and Ni is a unit vector. This is an S2, and U of N, so N will be the collection of Ni's, I in the picture, and Un is 1/2 some positive constant lambda 1, and I minus, so there is a summation here, Ij, which could be a distance 1, or which could be a distance square root of 2. So distance 1 or square root of 2 of Ni minus Nj square plus there is a sum over I, some numbers yi, which are the measurements, minus some function of Ni, which is not a very complicated function, but depends on a number of parameters that have physical significance about the composition of the material on Venus or something like that. And so this is the simplest version. There might be another parameter here, lambda 2, and you want to minimize this. Now, in fact, the actual energy or the actual function is a little bit more complicated, because when you have a mountain, let's say, there is always from a valley goes up, and you want to find these discontinuities in the gradients. The discontinuities in general, they are smoothed out of that, and you need to introduce some variables whether the discontinuity there is not. So really, in addition to n, there is a different variable here which tries to find out where the discontinuity is. That is, n and the other variable work together to find the discontinuities, and then I will not write down. But what's interesting here, there is another line PD problem that I did not study, and I think should be interesting mathematical problem. When you go to the continuum, this becomes the gradient, and this becomes an L2 norm. So if you like, so this is kind of the harmonic problem. You have gradient square plus an L2 function of y of x minus f n of x square. This is kind of the harmonic maps, and then you have this extra term. And in addition, you have interaction of this other variable with some coefficient here, with some other function. When this gradient is very large, it becomes 1. That tells you that there is a discontinuity. When this is smooth, like in the flat part, that's equal to 0, and there is some other term. Now, actually, I think this would be an interesting problem in harmonic maps. I have here from the plane into the sphere, but in where the harmonic maps are exactly this, but we have this structure here. And so there should be some existence theorem, actually, just when you add this term and what is the additional term. I think it's an interesting problem. It's a mathematical problem. And I did not zoom in because there are other things that I was more interesting. Okay. Now, so the way that you should think of this as a complicated thing, so if in one dimension, think of this function here that looks like this. And then, sort of goes like that and continues the same way this way, right? Now, I should say that these algorithms are mathematically interesting and have kept myself and other people busy for quite a while, but you don't want to use them in applications unless you run out of ideas. You will see in this one, you want to find the global minimum of u of x and your algorithm goes in the wrong direction, and then it jumps, it goes the wrong direction. So it takes ages really to detect this point. So this will be the optimization problem. Now also, I'm going to introduce this probability. So I imagine the u of x goes to infinity. I will write exact conditions divided by some normalizing constant, dx. And so the first problem, one of the problems is to find the global minimum. The other problem is to compute integrals of this form. And let's call this the expectation of f with respect to pi. So if you have a number of samples from this probability here, then you can approximate this. So let's say samples x1, x2, etc. Then you can approximate by an ergodic sum t from 1 to capital T of f xt. This approximates under reasonable conditions the expectation. Okay. Now, because we are in a very high dimension, and because of the complexity of u of x, there is no way of really deriving independent samples from this thing here. So you need an algorithm. Now, I'm going to present this mainly because once you have this, then you will see the problem that is involved for the global optimization. Okay. Now here is the basic idea both for the simulation problem and the optimization problem. The basic idea is this. You see, if I solve this equation, minus greater u of xt, let's say starting from some initial condition, then what will happen if I start from x0 here, then I will go down and go to the global, to the nearest local minimum. If I start here, I will go to the nearest local minimum. The idea is now to introduce some diffusion so that really you do not stay there, but you start diffusing and hopefully you jump over the barrier and you scan the entire space. By scanning the entire space, meaning you produce samples that more or less satisfy this, and then you will see by some modification of the diffusion coefficient, you can end up in the global minimum. So let me tell you how this, so I'm going to modify this slightly so that I do not stack anywhere, but I scan the whole space. I sample from the whole space. So there is a little bit of probability here, u xt dt, and I put a small some diffusion, a small diffusion, dwt, where this kind of a Brownian motion, a white noise. And the square root of 2 has been carefully chosen so that somehow when t becomes larger and larger, the solution of this equation, of this stochastic equation, is they look like samples from this distribution here. Okay? Now, for reasons that you will see in a minute, I'm going to introduce a parameter here. T, positive t, and then I will put this t here. Now, so this will start from some x0, either reflector or something, that will be distributed according to some probability distribution mu. That's the initial distribution. You can take it the delta function concentrated at a specific point, right? Now, the solution of this has an underlying distribution. The equilibrium distribution of this process here is exactly this. But I'm going to introduce this t for reasons that you will see in a minute in the globalization problem. So I'm going to here sort of to give precise condition that's actually condition on U that really the solution this produces correlated samples from this distribution here. Now the global optimization is the following. The global optimization is by choosing this coefficient of diffusivity to be time dependent. So dxt minus gradient u of xt dt plus 2. So I'm going to make this function of t, the capital T function of small t. And again, this is the white noise of the Brownian motion. And I start my process from some x0 or x0 that I distribute according to some probability mu x0. Now, if I take this thing here, if it is 0, then I stack in the closest local minimum. But if I take this to be going to 0 slowly, the theorem will show that actually I end up in the global minimum. Now, if you do, so I had another graduate student that I gave a two-dimensional analog of this, and he comes and he says, this algorithm is crazy because it keeps going in the wrong direction. And then it jumps on the other side and goes in the other direction. And if you are in 2 dimensions or even higher dimensions, you really take ages to go there. So there is a technical problem here. So these algorithms, although they are very popular and you see, sort of, and people that work here are proud, the bottom line is you don't want to use them in practice unless you cannot do anything else. So now, I'm going to give an improvement of this through some ideas from physics that apply to these structures here. These are versions, sophisticated versions of FFTs, fast Fourier transform, which they are under the name of Renormalization Group that was invented in physics. So the last 10 minutes, I want to indicate how that thing applies here. Now, there is nothing special about this. You will see this, you will lead us to some PD, actually, the stochastic. You will lead us to PD, which is known as the Langevin equation. You can take any, not any, but a more general diffusion processes and therefore differential equation. So let me indicate here. So I'm going to replace xt, and sometimes this is a useful tool in a number of places, dt plus square root of 2t sigma xt dwt. Now this sigma xt is ax transpose, and these are elliptic things, sigma ij, aij of x, xi, xj, c1, xi square, large or equal to c2, xi square. These are arbitrary parameters, functions, in fact. But this one has to see somehow my u, right, in order to get the right thing. The stochastic differential equation of the PD has to have some u, and the u comes only through the drift, and it has the following structure. It is sigma, so this is a vector now. Bi of x is summation over j at t dji xj minus aij, in fact ji, although these are could be taken symmetric, du xj. So if the aij's are just delta functions, then you get the Langevin structure. This coincides with that. Otherwise, you get the point is that the drift here depends on t, but the drift here does not depend on capital T. The T enters only. But you need the T in order to associate. That T that enters in the drift is very important to get an equilibrium measure that looks like this. Okay? So the theorems are no harder in this case than they are in that case, once you get the idea. Although in practice, especially if you are not in R, but you have some bounds, then it might be a useful device. Okay? So now let me, okay, so here it is. Yes, where is the page? Here it is. Now, I'm going to write, before I write down my first theorem, I want to write an operator down. Now, with every stochastic differential equation, there is a semi-group associated with that. The semi-group has a generator, which is typically an unbounded operator, and that the operator that associated with this is here. Is L minus T, the Laplacian, plus gradient of U gradient. Now, I'm thinking of this as an operator on L2 weighted with pi sub T, right? Pi sub T. This is a self-adjoint operator. It's a densely defined. It's how you call it? On the function it operates contains the C02 of RD, and it's non-negative. It's non-negative. Of course, these are involved some assumptions on U that I'm going to write in a minute. Okay? So, but I needed the definition of this. So the theorems are heavily, come down really to the spectral properties of this operator here. So here is the first theorem for simulation. Theorem 1, simulation. Assumptions on X, on U. On U of X. One, U of X has sufficient derivatives, so I need here at least 2 derivatives. Now, I'm going to write the theorems for RD, right? But I said the X could have the structure coming from the Xi's, and the Xi's could be in R, in which case it looks like RD. But instead of the values of Xi to be in R, could be bounded, in which case you do not have RD. Or it could be finite, in which case you cannot, this does not make sense, but you have to replace with a Markov chains. But so I'm going to write for RD because it's much easier to explain, and then I will in the proofs, I will tell you how one modifies the thing. Okay? So U of X goes sufficiently rapidly to infinity, and this is the property. So for simplicity, I will also assume that U of X, the infimum occurs at 0, that is bounded below. So U of X is bounded below, and I can shift the thing to be at 0. Actually, so because these are continuous, it goes to infinity, so it has to have some minimum. 2, that the gradient of U also goes to infinity as X going to infinity. Now, this is a very strange condition, the next one. It's a very strange condition. gradient u of x, where this conditional second derivatives, it is bounded below. It's bounded below. And the fourth condition is, of course, that this integral has to make sense, where now this becomes dt, and there is 1 over t here. This actually do not guarantee that this holds. So I assume for some t0 that zt0 e2 minus 1 over t0 u of x dx is finite, then it's trivial to show that then zt is finite for all t less or equal to t0. Less or equal to t0. And you see for the optimization problem, my t will go to 0. And for the simulation, I had t equal to 1, so which is fine. Okay? So this is the theorem. This is the assumption. This implies A this has a purely discrete spectrum. L has a purely discrete spectrum. And in fact, the spectrum looks like this. The first eigenvalue is 0. Then there is a gap between 0 and the next eigenvalue. And the next eigenvalue could have multiplicity, and so on and so forth. Now, these assumptions here, especially this, was to guarantee exactly this. This operator is an unbounded operator. So, and its spectrum looks like a compact operator, but it's not compact. What happens is these conditions were imposed in order the resolvent of some of a modification of this operator, the resolvent, which is bounded, has a discrete spectrum. Okay. B is for all f in L2 pi t. So t has been fixed in this theorem, right? And I assume that t is smaller than t0. T0. You have that e2 minus TL, e2 minus TL f minus the expectation of f with respect to pi t, which I defined there. The L2 norm weighted with pi t is less or equal to e2 minus t lambda 2 times f minus f L2 pi t. Pi t. Okay. Now, what this has to do with simulation, let me write a version of this or some consequence of this. Also, if I define ptx to be the probability that at time t, the solution to the stochastic equation is equal to x. Now, you see the e2 minus TL is the evolution that gives really this function in terms of the initial measure mu. So this actually is TL of x. You can put the mu on the side. This probability here, the probability to this equation for very large t looks like the probability of pi. This converges to pi t of x weakly as t going to infinity. So simulating, you see, producing these samples or solving this equation is basically eventually you produce samples that look like you are sampling from pi t. But these samples are not exact samples. They are not independent samples. So this is really what, like that. So that's the simulation problem. Ooh la la. So then maybe I should state the second theorem. Now, so let me get here. The second theorem is this. Theorem 2, optimization, is the following. So U of x satisfies 1 through 4. And so there exists delta 0. There exists delta 0 such that the limit as t, wait a second. Let me skip this because it will take like that. Now, if t of t, right? So I'm taking now the time-dependent diffusion, goes to 0 from above, monotonically, and satisfies t of t larger or equal to c logarithm of 2 plus t, that is for large t. Then ptx minus pi t sub t of x, of like that. This is the some norm, the variational norm, the variation of the two things, goes to 0 as t goes to infinity. So for those that don't know what the variational norm, you can take somehow sort of some weak converse or something. So what this tells you that now, okay? So this is equivalent to ending up in the global minimum because pi t of t of x is equal to e2 minus t of t, u of x divided by zt of t. Now this goes to 0. This goes to 0. Of course, there is this normalizing constant. U of x has global minimum at 0. So the only term as t going to infinity, this goes to if the global minimum is a unique minimum, it goes to a delta function considering the global minimum, right? You have to worry about what happens to this, but the only term that survives here is really the global minimum is unique. If it's not unique, it goes to something, and it goes to not to a probability concentrated on the global minimum, but to the probability concentrated on the global minima or the structure of the set of global minima. Then this provided that that C is larger or equal to some specific delta 0. This delta 0 is defined as following. Delta 0 is the limit as t going to infinity of t of t. Actually, you can put it like this. T going to 0 of t lambda 2 of t. You see, the spectrum here depends on the t that I have, right? On the t, the spectrum. And it is a property of Schrödinger operators that this thing here has a limit. That is, lambda 2 of t behaves or minus delta 0. Minus 1 over t delta 0. Now, this is not part of the theorem. This is it's known sort of, it's a hard property that's derived by experts in Schrödinger operators. Now, this operator here is not Schrödinger type operator, but there is a unitary transformation. There is a unitary operator that transforms this. It looks like a Laplacian plus some potential, like that. So that's now the proof of this. It is basically a spectral analysis. I mean, you just use, in order to prove this, you use the spectral theorem of the semi-group. But to prove this, actually, it does involve some energy estimates of the underpinning PDs. That is, this probability here, this probability satisfies a parabolic equation. Right? And the parabolic equation, has to be studied and proven like this. So a more detailed, not strictly larger than 0. The theorem also contains that actually converges fails for C smaller than delta 0. And it's not known what happens at C equal to delta 0. I believe to go either way. But one either has to construct examples or to prove that it goes in the right direction. And I'm not, I believe it goes in the other way, in which case, I mean, you have to construct examples in both directions. Okay, what's the renormalization group here? Just a few words. It's a beautiful structure. In fact, I was invited to construct a special chip of that until I convinced them that it's not worth. Because the idea is very beautiful. It comes from physics. It's very beautiful. But when you implement it, you don't gain more than 10%, which is depressing. 10%, sort of in this calculation is nothing. So the basic idea is this. So this is my graph, the simplest one. And in each I have an xi, which is sort of real, or the unit vector, or the thing. Now, you replace this by a coarser. So this is the crosses now is a smaller lattice. So I have 512 by 512, and then I have, sort of 264 by 264, and then 264 goes into 128 by 128. So I have a U of x on the dots. There are xi's in the dots. I'm defining a conditional probability what I associate with, I will associate some x's with the crosses. So for example, you could take the average, and probably that's not what we perceive. So you see, when you look at an image from far away, you see whatever you see. When you are close, you see whatever you see. When you move away, you go to a coarser thing, and then do you observe the average in the pixels, or you observe a nonlinear function of the average? And so it's over. So if you think of this to be black and white, then you take the majority rule. This black, 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 you put that black. If this black, black, white, you put this black. And if it is black, black, white, white, you flip a coin. I don't believe that perceptually we do the same thing. So I asked the, how you call this, to make an experiment like that. And it's not clear, but I believe nonlinear. So so I construct now, I start from the fine grid, then I construct a coarser and a coarser and coarser. So I have the one of U of x divided by z. I define a probability x prime now are associated with crosses. I integrate out x, and that gives me a minus u prime, x prime. Turns out the z to be the same. the Z to be the same. So this is kind of an energy associated with crosses, and then you go down and down. Now, if the x's are discrete, there is a theorem that tells you that if I find the global minimum in 32 by 32, then I use this to find the global minimum in 64 by 64. I use this to find the minimum in 128 by 128, whatever, and then and so on and so forth up to 5. And as a concept, it should really speed up the algorithm, but it does not. The point is the following. Intuitively, really, as I had like that, the problem is a random walk is a random walk. It starts here, it goes down, and then it diffuses locally. And there are, when you are in high dimensions, there are small scale phenomena and long scale phenomena. The small scale phenomena, they propagate quickly. But to get to the long one, therefore somehow you have to have large movements in your RD, basically. Your RD movement. And this is like the FFT, fast Fourier transform, and the normalization are conceptually the same, except the normalization, they try to make fast movements. For those that they know numerics in PDs, there is, gosh, how do they call that? A multigrid, where again you construct, but the multigrid does not do an integration like this. It does a different trick, and that also does not work very well. People have explored that too. Does not work very well. So, I'm done? Or I have more? Sorry? I'm done?
Technically, yes.
Okay, so if you have some questions and our chairman permits it.
So let's thank Basilis.